Hi, everybody. So you've been working on your test? Hi, I wrote it. And I dig me some parameterized by arc length curves. So I made up one so that I'm not doing the one that's on the test, but you have a question on the test where you have a curve that's parameterized by arc length, and you have to verify that its R prime has length 1. So look at this massive pile that I've created for you today. Let's look at R. And I'm not going to graph it because I'd have to fire up my scientific workplace thing, but maybe we'll take a look at it in class. I just can't fit a graph on the board with this other stuff. The first coordinate function, we're in 2 dimensions. First coordinate function is the integral from 0 to square root of s of the square root of 24u minus 36 du, comma, 6 square root of s minus s. So this is a function of s, and this, believe it or not, is a function of s. If you were to do this integral and evaluate it, it would be a function of s. S would be the variable. But it's written like this because when we find r prime, you have to take the derivative of each coordinate function. So the derivative of the first coordinate function, I want to recall something from fundamental theorem of integral calculus. When you have to take the derivative with respect to s, in this case, of something, an integral that goes from 0 to s, or in this case, square root of s, and then you have the integrand function f of u du, the answer is f of that function, square root of s, in this spot, but chain rule says this is now the inside. This is what's so weird about this theorem. This is the inner function. It doesn't look like it's on the inside, but it is. So by chain rule, I have to multiply by the derivative of that. The derivative of square root of s is 1 over 2 square root of s. That's what this is. So we've got all that stuff from the fundamental theorem of integral calculus. Let me see if I can get everything in the picture a little bit better there. Can I get that in there? Yeah, that looks a little better. There's a 0 down below that integral. Lower limit of integrations is 0. And do we get the full thing of that? Yeah. Anyway, this piece here is what's over here. That 1 over 2 square root of s is the chain rule piece. It gets squared. And then this square root pops out like toast, and it gets squared. So that's a 2 over 2 power. That 2 over 2 power is a 1. So I don't have to write that in. And this becomes just a 1 over 4s right there. So if you don't mind, I'm going to do the 1 over 4s thing right in this spot. So I've got a 1 over 4. Oh, that's a square root of s. My fault. God dang it. I thought I had prepared so well for you. All right, square root of s there. And then I've got a 1 over 4s right in that spot. I'm going to erase this. So that came from squaring this 1 over 2 square root of s. So it's a 4 and an s down below. I got to square this thing out. So let's square this out. I'm going to get a 9 over s minus 6 over square root of s plus 1. So that's what this turns into. Now let's see what this boils down to. I get a 6 over square root of s, and I get a minus 9 over s. And don't forget that plus sign is still there. So the 9 over s's cancel. The 6 over square root of s's cancel. And all that's left is a 1. And that's why this thing's parameterized by arc length. Because this whole mess has been set up so that this happens. All that's left is a 1. And you do the integral of 1, or sorry, the square root of 1 is 1. There's no ds on the end, it's not an integral. Anyway, so you do the arc length formula on this thing, and you get square root of 1, which is 1. R prime is 1. So you can watch this video a few times and look at the pieces. That's the most I'm going to say about your test. I think the problems are eminently doable. Your arc length problem is much easier than the one I just did. But remember, that's what you're trying to get. These few steps, make them happen. I took the test. Everything should work. You shouldn't have any difficulties. Let's take a look at some new stuff. I'm going to introduce you to a new operator, and we'll see this in class. We're going to be using this a lot. When you have f of xy equals, let's say, x squared minus y squared, we're going to have a new operator. It's called the gradient operator. The gradient acts on a function. It has to be a multi-dimensional domain. And in this case, it is the partial with respect to x of the first coordinate function. Sorry, the partial with respect to x of the function, comma, the partial with respect to y of the function. So the gradient takes a function with a vector input, scalar output, and gives you a vector. So in this case, I have 2x, comma, negative 2y. And that's what grad f, they call it grad sometimes when they're trying to say it fast. Gradient f is this. It has uses, very cool uses. The only use I'm going to show you tonight on this video is we're going to do the directional derivative. So I'm going to leave this example up to the side here. I'll just have f of x equals x squared minus y squared. And grad f is vector 2x comma negative 2y. I'm going to erase, and you already know what x squared minus y squared looks like. It's not a saddle. If z equals x squared minus y squared, you've got the, it would have to have, if I have in one direction z equals, if you set a value for z, 1 equals x squared minus y squared. Yeah. Oh, it is a hyperbolic paraboloid. Yeah, it's a hyperbolic paraboloid. So let's examine this new animal. It's called the directional derivative. And it gives you the slope of the tangent to the surface at this point in the unit direction. And the actual formula is grad f evaluated at x0, y0 dotted with a unit vector. So the unit vector, it's got to be a unit vector right here because it doesn't contribute to the size of the calculation. So let's do this example. Let's say I have, let's make just a little table of values here. So I have the point 0, 0. And if I have the vector 1, 0. Okay, so here's what we would get. I would get the big D sub u of f at 0, 0 would be 0, comma 0 dotted with 1, comma 0. 0 plus 0 equals 0. Now, why would that be an acceptable answer to us? Oh, it makes sense. Because no matter, if I'm looking in this direction, I get a horizontal tangent. And likewise, if I'm looking in that direction, I get a horizontal tangent. And that's the same as doing this. I get a horizontal tangent with that one too. And in fact, if you look at it, because of the zeros parked in both these places, at the origin, no matter which way you're looking, you are at a bump. Now, it might be the bump concave down. It might be the bump concave up. But you've got horizontal tangents all the way around at that point. Well, let's pick another point. Let's pick the point. Now, it's got to be a point, let's say 1, 0. So 1, 0 is 1 along the x-axis. And that would be 1 on the x, 0 on the y. Z is going to be 1. So we're up on this part of the slope. We're up here. The z coordinate's positive. So let's see what happens if I do the way it is written. So now it is the directional derivative at 1, 0. So I get the vector 2 comma 0, dotted with 0, 1. And you can see that comes out to be 0. So at this point, but facing in this direction, I get a horizontal tangent. And you can kind of imagine it. If you were walking on that hillside, in one direction, it's sort of like when you're walking on a hillside, there's a direction you can face where you have a horizontal tangent. But if you turn in another direction, 1, 0, I'm not going to get 0 this time. I'm going to get the same evaluation, putting in the 1, 0. I get a 2, 0, but I dot it with 1, 0, and I get the directional derivative as 2 in that case. So in this time, I must be looking uphill. I must be looking in that direction. I'm looking uphill. So my derivative says, oh, you got a slope of 2. So one more. Let's say I'm at the point 0, 1. So now I'm not there. I'm down here somewhere. Because at 0, 1, I've got a negative z coordinate. So I'm down here. If I look in the direction 1, 0, let's do this problem again. So I've got the 1, 0, but the directional derivative, the gradient evaluated at 0, 1 is going to be 0, comma, negative 2. And this dot gives me 0. So I'm standing at that point, but I'm facing in a direction where I'm getting a horizontal tangent. I'm facing in a direction where, in that direction, the hillside doesn't change. I can kind of creep along that hillside and stay at the same height. But all I have to do is face a different direction. Same point, different direction. I think it's 0, 1 this time. And you can see I'm getting a slope negative 2. And that's at this point facing downward. I'm facing downward. I see a negative slope. The surface curves away from me. So this is fairly standard notation. This is not like that projection conglomeration, that comp thing that this guy made for projections that I completely ignored because it's not standard. This is fairly standard, but there are other ways of writing directional derivative. But I see this one. I see that notation in math books and math journals besides our own. So that's one use of gradient. And we saw the other one in class where for tangent plane, you can write the equation for tangent plane in terms of a gradient dotted with something. So the two examples I've given you, gradient dotted with something. And that's our show for this evening. Work on your test, spend an hour and a half on it, and get it right so it's easy to grade. See you guys on Wednesday.